Okay, so I want to talk a little bit about conservation of energy and how we can account for conservation of energy both translationally, which is kind of like the way most people start out learning about conservation of energy. We can also talk about conservation of energy rotationally. So let's just talk about what both of those mean. So we need energy to do stuff, basically. Energy is just like the juice that we use to make stuff happen in like our physical world. So we have this kind of motion, which is just like moving things across, like maybe sliding this cannon across the paper. And nothing's really going to be rotating. We're just kind of translating the cannon across the paper, and that's fine. We know how to do that. We also have this kind of motion where we're going to spin the wheel and it's going to rotate. But again, nothing happens for free. We have to give it some energy, and in this case, it's getting the energy from my finger pushing the wheel, and the wheel's going to spin. And again, that's just another fancy word for rotating. So it's just rotating, and that takes energy, but it's not moving across the page, and it's not. It doesn't have like a track for my finger, so it's not translating really. It's just getting energy, and it's using that energy to spin the wheel a little bit. Now we could have both. If my cannon like rolls across the page, I give it a push from my finger, gets energy from my finger, and then it uses that energy to both translate and rotate. Okay, so now that we kind of have those terms defined, let's talk about conservation of energy. Well, we know from past physics lives that energy has to be conserved, and what that means is that the change in kinetic energy plus the change in potential energies, they gotta equal zero, right? They gotta add up. So all that means is that if I have my pencil and I'm gonna lift up my pencil, I'm giving it potential energy. When I drop the pencil, the kinetic energy it has at the end is going to be the same as the potential energy I just stored it up with. So that we agree that happens. At the end, it had like a nice click, bounce up a little bit. Energy is conserved. Story checks out. We could have kinetic energy that is translational. We could also have potential energies. Now, potential energy in a rotation, maybe if we like incorporated a spring in there, that might make sense. But we're not really going to have potential energy that is rotating. Like this wheel's not moving. It's not going to spontaneously start moving because of the potential energy stored up in it. It's just doesn't have any. So unless we use gravity or something, but even then, that's not really the wheel storing potential energy. We have gravity. So our potential energy might be things like gravity or springs. Maybe chemicals might store energy, but as far as the wheel is concerned, it doesn't have any inherent energy stored up. So we want to keep that in mind as we set up our equation. So remember, we're talking about the changes in these energies. So we want to keep in mind that we're taking our final kinetic energies minus our initial kinetic energies plus our final potential energies minus our initial potential energies. Okay, and that's going to equal 0. All right, so now we can take everything that's negative and kind of move it over there. Nothing surprising there. We've seen that in our minds a lot. If we think about it, it just kind of makes sense. That's fine. Okay, great. Now we've got all that established. Let's take a look at our problem. A hoop is rolling without slipping, so without slipping, no friction, along a horizontal surface with a speed of 8 meters per second. It starts up a ramp that makes an angle of 30 degrees with the horizon. What is the speed of the hoop after it has rolled 3 meters up the ramp? So we're looking for the speed of the hoop. What is the speed after? So the final speed. We want to know the final velocity of this runaway hoop. So we have a couple things we want to do. So first thing I want to do with any problem is draw a picture to make sure I know what's going on. So I have a hoop, a lot like this wheel without the spokes in there because we don't want those spokes. And it's also not attached to anything. So again, we don't have the friction on the axle. We just have the hoop. So it's not slipping, so we have no friction. So this hoop is translating at 8 meters per second. It's going to go up an incline. And this incline, they tell us, has a inclination of 30 degrees. It makes an angle of 30 degrees. And we want to know what is the speed after it's gone 3 meters this way. So after it's gone up the ramp 3 meters. So up the ramp 3 meters. Okay, so instantly we can see where our energies might be coming from. We can see that it's going to take some energy to make the hoop rotate. We can see that it's taking energy to make the hoop go 8 meters per second to the right in this case. And we know it's going to take energy to come up this hill, and this energy that it loses up the hill is going to be converted into potential energy. Potential energy. And the potential energy isn't going to be given by however far it goes up that incline, but how far it goes up away from the surface of the Earth. Gravitational potential energy is going to be our weight times the height. So our weight times the height is going to be our potential energy at this point, right? Okay. So let's find how much kinetic energy it has at the beginning, and then we're going to convert all that energy into potential energy plus whatever kinetic energy it has at the end. Okay, so that makes sense? Let's write all that out. Okay, so we have the kinetic energy that is rotational at the beginning. We have the kinetic energy that is translational at the beginning, and that's going to be equal to the potential energy that we have at the top of the incline plus the leftover kinetic rotational energy at the top of the incline plus the kinetic energy that is translational at the top of the incline. So this is initial. Excuse me. So we have kinetic energy rotationally initial plus kinetic energy translational initial, and then we're going to convert that with the equal sign to potential energy, then whatever kinetic energy rotationally it has left over, whatever kinetic energy translationally it has left over. All right, so we know that kinetic energy for things that are translating is 1/2 mv squared. Easy. We know that things that are translating rotationally are going to have this formula, 1/2 moment of inertia, rotational velocity squared. Rotational velocity squared. So we have 1/2 the moment of inertia, omega squared. We know that omega is equal to the velocity over the radius, and that's just because we're saying that for every rotation it's going to end up going whatever the distance of the circumference is, so it's dependent on the radius. So every time it rolls one rotation, we end up going one circumference along the track. So we can substitute that in. We also know that for a hoop, the moment of inertia is just going to be mr squared. So that's pretty easy. We can just put that into the equation that we have down here. So our rotational kinetic energy at the beginning is 1/2 times v over r squared. And again, that's just taking the rotational kinetic energy formula and putting in our moment of inertia and the rotational velocity. We're going to square it. Okay, so we got these guys added up, no problem. Let's figure out what's going on with our end result. At the end of our situation, once it's rolled up these 3 meters, we have a final potential energy. Okay, so we have a mass. That's just gravitational energy. We have a mass of the wheel again. We have gravity. That's easy. And we have a height. Now the height isn't going to be 3 meters because that's just how long it goes along this incline. If we see this ramp, we can see it as a triangle, and we want to know the height. We want to know this side right here. Well, it's going to be shorter than 3 meters because that's the hypotenuse of this triangle, and that's the longest side, so it's got to be shorter. So we're going to say, okay, our angle is here, 30 degrees. Is it the adjacent angle, or is it the opposite angle we're looking for? I'm going to go with opposite. Okay, now we're going to add to that the kinetic energy it has rotationally, spinning, at the end of our situation. So once it gets to the top here, we have a spin. Ooh, that's not a great circle. We have a spin, so it still has energy rotation. The angular velocity, which for us is velocity over translational velocity over the radius. So we have v over r squared, and this is our final v, right? That's what we're going to get at the end. So if we want to come back to this side, we can label these v's initial, or we can just leave them by themselves because it's the only initial we know at the beginning. So we want our final velocity at the end. Great. Radius stays the same. It's not like our wheel is growing, so radius is fine. We'll just leave it alone. Mass, again, is not getting heavier. We're just leaving it alone. Okay, plus our kinetic energy from the translation. Okay, great. So let's just do some algebra, and we'll cancel as much as we can out, and that'll make our equation kind of condense, and it'll be super easy after that. Plus, same thing down here. I'm just going to bring it down. 1/2 mv squared, and that's initial, again, velocity. It's going to be equal to our gravitational potential energy. That's mg. We have 3 meters, but we know that sine of 30 is 1/2. So 1/2 of 3 meters is 1.5 meters. Easy. Okay, so we have now our kinetic energy at the end that is being used to rotate the wheel, and that is 1/2. Well, we see the same thing's going to happen over here. We see that the rotational velocity is going to allow us to square this r on the bottom, and that's going to cancel out with this r right here. So 1/2 m, r's cancel out, and v still gets squared, so m v final squared. Okay, great. I'm seeing a pattern here. So we have, again, 1/2 mv squared, but the final velocity, 1/2 mv final squared. Great, okay. Well, 1/2 of something plus another half of that same thing is just one of that thing. So we can combine these and get 1. We're just going to add them together. So we end up with just mv initial squared is equal to the gravitational potential energy, mg. We can leave this as h now that we know what h is, or we can leave it as the actual distance. I'm going to substitute this in as h. So we know, looking at our picture again, we have h right here. H is just 3 sine 30 meters. There we go. Okay, so mgh plus, again, 1/2 of something plus 1/2 of that same thing. If I have like 1/2 of an eraser and I add it together, like if I have 1/2 of an eraser right here and I add it to itself and I add the other half to it, I can see how that would combine to make just one solid eraser. Easy. So we're just going to take away these halves, combine them, and get the final squared. Okay, hang on. We have coefficient of m for all of these terms. So mv initial, mgh, mv final. So let's get rid of all these m's. We're going to divide everything by m. Awesome. So now we're saying it's turning into a really easy problem. Looking for again, we want to know what is the speed of the hoop after it has rolled 3 meters up the ramp. So the final velocity of that hoop. Well, good thing they didn't ask us for the rotational velocity because we just spent all this time getting rid of it. Good thing we need to know the translational velocity, which is right here. Even if we had to find the rotational velocity, it wouldn't be a problem. We would just use the same conversion we use for the analog up here of omega being equal to velocity over the radius. Okay, so we're going to solve for v final. We get that v initial squared minus gh. You can square root that whole thing, and that's going to equal our final velocity. Awesome. Okay, we can, at this point, just kind of plug things in. So we know that it's going 8 meters a second to start out with in our picture. We know that to be true. We know it's going to be going some velocity that way, but we don't know how fast. And we know the radius of the, oh, wait, we don't know the radius of the hoop. How can we solve this problem if we don't know the radius of the hoop? Well, if you notice, when we did our conversions, we ended up canceling all of our radiuses, right? Radius got squared, so we're able to cancel out. So in our end formula, we don't even care what the radius of the hoop is. It could be a hoop this size, or even like maybe if I trace this right here, it could be this size. I don't even think that'll fit. Oh, it fits a little bit. This size. It doesn't matter how big the hoop is because our formula shows that it doesn't have anything to do with the final velocity. All it's dependent on is the initial velocity and the height of the ramp. Okay, so we know that the height of the ramp is 1.5 meters, and that's just 3 sine theta. We know that the velocity initial is 8 meters per second. And of course we know what g is. That's 9.81 meters per second squared. That works out. When we square root these guys, we're going to square root both terms, and we'll end up with meters per second for the final velocity. Awesome. I don't know what we're waiting for still. Let's go to it. So 8 squared is 64, minus 9.8 times 1.5 is 14.7, let's say 2. And we're going to square root both of these combinations, and we're going to get the final. Okay, so finally, I'm not going to use my mind to use that kind of arithmetic, times 14.72. We'll square root that, and we'll have that our final velocity is still 7.0 meters per second. Our problem only gives us room to use one significant figure, so I'm going to change that to 7 meters per second. Awesome. So that's how you use conservation of energy in a wheel rolling up a hill scenario. Well, it isn't just limited to this scenario. You can use it for any kinds of scenarios, and I encourage you to kind of like pause and make up your own scenario and kind of predict what would happen and work out how we might do the math for that situation, your own situation. Well, good luck. That was awesome.